Good morning everyone. You can see our topic. It is the refraction of light through a lens, and here we will study about the formation of image by a lens with the ray diagrams, and also we'll study about the lens formula. We'll start from here, a point source of light. You can see this is a point source and it is sending a number of light rays in all the directions. So we can say that a point source of light is capable of sending infinite number of light rays in all the directions. Now if we suppose this point source we are situating in front of a concave or convex lens. So here the lens is, this point source will send a number of light rays to the lens, and all those light rays will refract from the lens. But in ray diagram it is not possible to draw all the light rays, so we will take only three light rays. Those are called the principal light rays. You see here. Here we'll study the formation of image by a lens and the ray diagrams. And here we are taking the point source. This is the point source A, which is sending a number of light rays. All the light rays are going toward that side are not taken, but we are taking the three light rays incidenting on the lens surface. This is a convex lens we have. Those three light rays are called the principal rays. Here we have the first, second and third principal ray, as you can see. The first principal ray is the light ray which is passes from the optical center of the lens and remain undeviated. The second principal ray means the ray which is incidenting parallel to the principal axis, and after refraction it will move toward the focus of the lens. And the third principal ray means the ray which is coming from the first focal point of the lens and incidenting on the lens, and after incidenting on the lens after refraction it will emerges parallel to the principal axis. Okay, as the ray is coming from this first focal point, so after refraction it will take this path which is parallel to the principal axis. So here we have the three principal rays incidenting on the lens and the three refracted rays also. But here all the three refracted rays are actually meeting at a point A dash. So this point A dash is the real image of this point A, and these rays after A dash, all those rays after A dash are if here we are standing, we will find that all the rays are originating from this point A dash. So this time this point A dash is acting as a source, which is not the actual source but the image of the source. Correct. Now this thing we'll see in the concave lens. You see here, this is the point source and it is sending the light rays. This is the first light rays passes from the optical center, remain undeviated. This is the second principal ray incidenting on the lens, and here it is diverging toward that side such that it is coming from the focus of the concave lens. You have the idea that whenever it is a concave lens it has the diverging nature, and the ray if the principal ray is incidenting, the ray will diverge in a direction such that it is appearing from the focus of this concave lens. Now this is the third principal ray which is directed to the first focal point of this concave lens, and as it is directed to that side, so after reflection from the lens it will take a direction, it will emerges in a direction parallel to the principal axis. So now we have the three principal rays here and we have the three refracted rays here. But if we are standing here, we will find that all the three refracted rays are coming to our side and they will not meet somewhere because they are diverging, they are going away from one another. So when we stand here, we will try to find out that from where these three rays are coming, which is the common point from where these three rays are coming. So we all are unable to predict the actual position, but we will find the appearance of that position from where the rays are coming, and the appearance is here. For that we will produce the line backward and we'll find a common point, and this point is inside the lens, which is the virtual point. Okay, and from this point these rays are appear to be coming out. This point is called the virtual image of this point A. Correct, which is acting like a source here in that case. Now you see here we have an object here, this is AB. So an object itself consists of a large number of points, As you can see, we have shown 2 points here, A and B. There may be a large number of points in between this A and B, so we are taking only 2 points. The top point, for the top point A, we have the image here, correct, and for the bottom point we will try to find out the image. For that we will take two rays. This one is the ray we have taken incidenting on the lens, and as this is a convex lens, so the ray after incidenting here, after reflection, it will converge and it will bend toward the principal axis. Another ray we are taking which passes from the optical center, so then we will get the two rays. See, the two refracted rays are meeting at a point, correct. So here we will get the position which is the real image of the point B, from where the light rays are coming, correct, and it is taken as B dash. The same thing we will do for the concave lens also. You see here, this is the point B, the light rays are incidenting here first, and as it is a diverging lens, it is a concave lens, so the ray will diverge toward that side. So we will produce a line backward here, and then after we'll draw one more line which is passes from the optical center and remain undeviated. So there is the point we have got, which is the image of this point B dash B. Okay, B dash is the point which is the virtual image of the point B. Why virtual image? Because you see, this is one ray and this is the another refracted ray. Those are actually not meeting, but those are appeared to be coming from this common point B dash, and that's why this B dash is the virtual source of these two rays. So this is taken as the virtual image of this point B. Clear? Now how we will draw the ray diagram for the object taken at different positions. So here we have taken the object beyond 2f1. Beyond 2f1 means here, see, this distance, this is the first focal point and this is the second focal point. From optical center to first focal point, or from optical center to second focal point, we are taking the distance as focal length. Here we have taken OF1 as minus f. See, OF1 is minus f because, see, here we are going left from O to F1, that is we are going left. If you try to understand how we will take the distances in the number line, here we are going left, so that's why we'll take the distance with a negative sign, correct. This thing we'll know in sign convention also, but here you just try to see that we are taking the object here in B, okay, which is beyond 2f1. Beyond 2f1 means you have the idea that focal length is half of radius of curvature. So this is f and this is f, so this total distance is the radius of curvature. I mean O into 2f1. So this is O to 2f1 is, you see, 2f. So 2f means the radius of curvature. So that's why I have given here in between center and infinity. So this is the position of the object, and this is the position of the center of curvature, and here we have the infinity. So in between infinity and center of curvature we have the object. Now you can see we are just taking the two principal rays only. This is the first principal ray and this is the second principal ray, correct. And when those are incidenting on the lens, see, these are the two refracted rays. We are getting the position of A dash here, and after getting the position of image, after getting the position of real image as A dash, we are just drawing a perpendicular on the principal axis to get the position of this point B, which is B dash. So what we got here, A dash B dash as the image of this point object AB. Now you see this image. The characteristic of this image is, as the rays are actually meeting, so it is a real image. You can see it is an inverted image because you can see A dash is here and B dash is here. So it is real inverted, and here it is smaller than the object. So we'll say that it is a diminished object, diminished image, correct. The same position we are taking in front of the same position of object we are taking in front of a concave lens. Here you see these are the light rays incidenting. After this is the second principal ray, so this is the refracted ray diverging away. So we have produced the ray backward. This passes from the focus point, and this is the first principal ray which is passes from the optical center. So here these two points are intersecting, these two lines are intersecting, and this is the position of image of this point A, that is A dash. And after drawing a perpendicular on the principal axis, we are getting the B dash also. Here this F means the distance from this O to F2, correct? No, so A dash B dash, that we got the image formed by this concave lens of this object AB. Now here what we are getting, the rays are actually not meeting. This is one refracted ray and this is another refracted ray, so they are actually not meeting. So we have just produced this line backward, so that we'll get a appearance of this point from where the light rays are originating. And that's why this point is the image, I mean it is the virtual image. Okay, so here A dash B dash is the virtual image, erect image, and here what we are getting, it is a diminished image of this object, correct? Now in this way we will put the object at different positions. You see here we are putting the object at 2f1, that means exactly at the center of curvature. 2f1 means center of curvature. Okay, so this is the center of curvature, and see the light rays are incidenting. So here again we are getting the real inverted image, but this time the size of the object is size of the image is exactly same as the object in that case, in the case of a convex lens. Okay, here we are putting the same condition in front of a concave lens. This is the center of curvature of 2f2 where we are putting the object, and these are the light rays incidenting, and we are getting the image here. So here we are getting again a virtual image, erect image, and a diminished image. So in this way we are putting again the object at another position in between center and focus. So you can see this is what we got. Again here we are getting real image, but this time it is magnified image because this image is greater than the object in size. Here you see when the object is at F, you see it is a special case. This is the position of the object, and these are the light rays. This is the first and this is the second principal ray, and you can see this is the first refracted ray and this is the second refracted ray, and those are parallel to one another. So where they will meet? They will meet at infinity. So we will write a real, inverted, and highly magnified image at the infinity, because these two rays are parallel rays, they will not meet. Even if we produce the rays backward, they will not meet. So we will take that those rays will meet at infinity, and where we will get a real, inverted, and highly magnified image, correct? And here you see this is AB as the object placed exactly at the focus of this concave lens. So what we will get here, this is the first principal ray and this is the second principal ray. This is the refracted ray, and this is the refracted ray produced backward, passes from the focus. So we are getting a point here. So here you can see this image is virtual, erect, and it is exactly half of the size of the object, correct? So this is the nature of the image formed by a concave lens. Now here we have a question that when the object is in between focus and O, and we have this one, and the lens is not placed here, you have to place the actual lens. That means you have two options, whether you can put a concave or a convex lens. So what lens you will put here? What you are seeing here, that this is the ray and it is diverging away. So if it is diverging, so a divergent lens will put, divergent lens means a concave lens will put here. We have one more question. You can see we have the position of the object is given, which is in between F and O. So this is the object, light rays will incident. Okay, this is a convex lens, so light rays will incident here in the convex lens. We will draw the first and second. You see this is the first principal ray and this is the second principal ray, and these are the refracted rays. Now you see this refracted ray will pass from the focus, but they will not meet because they are going away from one another, you see. So that's why we will produce these two rays backward in order to get the appearance of the image, correct? The apparent position from where the light rays are coming, from where these refracted rays are coming. So if we produce the lines backward, so we'll get a point here. you see here. Correct. This is the position which is the image of this A, that is A dash, and we will draw a normal on this principal axis, so we will get the image of this point B as B dash. Correct. So now what we are getting? We are getting a virtual image in the case of a convex lens, and virtual erect, and this image is a magnified image bigger than the object. Correct. And you can see the position of the object is in between 2f1 and f1. Now we'll see the measure of distances, that is sign convention. You see, if you have the idea about the number line, and here optical center is taken as the 0, so when we go to the left, we'll take the distance with a negative sign. When we'll go to the right, we'll take the distance with positive sign. Now every time we are putting the object on this side, okay, so it is on the left side, it is at the left side of the lens, so that means this distance, which is, that is the distance from where, the distance of the object and the lens, we will take with a negative sign, because the distance we are taking from O to B. So OB, you can see OB is minus U. Remember that object distance always we will take with a minus sign, so this minus U is the object distance. U is the object distance, but we have to mention the minus sign, as because the object is at the left side. Now for this particular condition we are getting the image here now, so this image distance, that is from O to B dash, it is taken as the image distance, as it is to the right of this lens, the image is to the right of this lens, so we will take a positive sign here. V is the image distance and we are taking a plus sign here. Why? Because the image is at the right. If the image form at the left, we will take V with a negative sign. Correct. Now one more thing, we have a convex lens here. So for the convex lens, the focal length is always positive. So this OF2 we will take as a focal length of convex lens. For a convex lens, focal length is always positive. See here, focal length is always positive for a convex lens. And for a concave lens, we will take focal length as negative. Okay, now you see this one, a lens formula. The lens formula establishes a relation in between U, V, F and R. Here R means the radius of curvature. You see, you have the derivation, you can see the derivation in your book. Here the lens formula is given as 1 by V minus 1 by U is equals to 1 by F. And you have the idea F is the half of radius of curvature, R means radius of curvature. So we can write, here we have F is equal to R by 2, so we can write 1 by F is equal to 2 by R. So we can rewrite the lens formula as 1 by F minus 1 by U is equals to 2 by R. In the place of 1 by F, we have taken 2 by R. Correct. We have a question here. A lens forms a virtual image at a distance 30 centimeter when the object is taken at a distance 10 centimeter. So here it is given that distance are taken from the lens. Calculate the focal length and identify the lens. So here what you will do, here we are getting, this is the image distance, virtual image. So this virtual image means at the right side, left side of the lens. Virtual image will form to the left side of the lens, so this 30 we will take with a negative sign. Correct. V is equals to minus 30. Object distance is 10, so object distance always taken with a minus sign because object is always to the left of the lens. So minus 10 will take, U is equals to minus 10, and then we will put the values here, 1 by minus 30 minus 1 by minus 10, and then we will solve for F. And if we'll get F with a plus sign, then it will be a convex lens, and if we'll get F with a minus sign, it will be a concave lens. Remember that focal length is positive for convex and it is negative for concave. Don't forget this. So if we'll get the focal length, so we'll write the focal length, and with the sign we can determine whether it is a concave or convex lens. Now you see here, linear magnification, which is the ratio of image size and object size. Here we have magnification m is equals to image height by object height, or we can write the relation as this way also, image distance by object distance. So for any lens, whether concave or convex, we have magnification is equals to h dash by h, or it is equals to v, that is image distance, by u, that is object distance. Now you see one question is given here, the same type of question, but here I have given 15 mm sized virtual image. So 15 mm size virtual image, so that means h dash means image size. So image size we have, when the object of height 5 mm, so that means h also we have, so 5 by 15, we have 5 by 15, so 5 by 15 we'll put, and here we'll put object distance we have 10, so we can get the value of v, and it is a virtual image, so we will be negative, and then after we will calculate the focal length by using the lens formula. And also we can identify the lens by predicting that what is the sign of the focal length, whether it is positive or negative. Now see this one, the power of a lens. Power is the reciprocal of the focal length of a lens, and this focal length is to be taken in the meter with the unit meter. So P, which is the power, is equals to reciprocal of focal length, that is 1 by f, where f is taken in meter. If centimeter, if the focal length is given in centimeter, we have to convert in meter and then we'll put. So the unit of power of a lens is diopter. One diopter is equals to 1 per meter. So 1 per meter I have given. Why? Because you have to take in meter. Okay, so it is better if you remember the formula, P equals to 1 by meter. Diopter is equals to per meter or 1 by meter. Correct. So then you will take the focal length in meter, because in your questions the focal length is generally given with centimeter, so you have to convert this in meter. So remember this, don't forget this. And here note that P is positive, power is positive for convex. Why? Because focal length is positive for convex, so 1 by f will also be positive. So power is positive for convex and negative for concave lens. Now we have this question once again, the same question. Okay, and here we have to predict, we have to determine the focal length, the power, and we have to identify the lens. So see, I have done the calculation here. We have taken the image distance as dash, object distance as, object height as 5 mm, and image distance as 15 mm, image height. So, and u is also given as -10. So while using the formula of magnification, there is no any use to put the signs, because it is a ratio only. So 15 by 5, h dash by h, ratio of image height and object height is equals to v by 10. So v will get 30 centimeter. But here it is given virtual image, no? So that's why v will be taken with a negative sign. Correct. So this one we will take with a negative sign. So -30, v is -30. And now 1 by f is equals to 1 by v minus 1 by u. U is negative always, object distance. So we'll get f 15 centimeter with a positive sign we are getting. So that means it is a convex lens. Okay, since the focal length is positive, so it is a convex lens. And now as we have the focal length, we can get the power also as 1 by f. So it is, see, you can see we have just converted this centimeter into meter as 0.15 meter, and then after we have calculated as plus sign has to be given there. Okay, while writing the power P, plus sign or minus sign has to be given there, because this plus sign or minus sign will tell what type of lens it is. As because here focal length is positive, so that means it is a convex lens. So we'll put a plus sign here, because convex lens the power is positive. So 6.67 diopter is the answer. It is the power of this lens. So this is all for today. Thank you, class.